In this video, I will be explaining some higher order Newton codes formulas, namely the Simpson's rules. So Simpson's rules approximate the function that is to be integrated not with a first order polynomial, such as the trapezoidal rule did, but it uses a higher order polynomial. So you have a number of Simpson's rules, depending on which order you choose. But here depicted are the two rules that I will be discussing and that are most commonly used as well. So in the first figure A, you'll have a second order polynomial that will be used to approximate the function that passes through 3 data points. And this is Simpson's 1/3 rule. And here the integral is approximated calculating the area under this parabola. And in figure B, a third order polynomial going through 4 data points is presented. And this is a depiction of Simpson's 3/8 rule. So first I'll be discussing the 1/3 rule. So the 1/3 rule, like I stated, uses a second order polynomial to approximate the function under the integral. So we can represent that as this. We have this function f of x that is to be integrated again, and in this case we use a polynomial that we depict with p2 of x, second order polynomial. And we can write this polynomial using Lagrange format in this case. And recall from the video of Lagrange interpolation that we can write a second order polynomial like this. So yeah, these are the L functions times the y values. Then we can integrate the expression for the polynomial in our last slide, after which we obtain this approximate integral. I will not do the derivation, but you can do it at home if you'd like. But here we'll see that the integral is approximately equal to h over 3 times this summation. And h is the step size again. So if we have a single application, then h is going to be equal to b minus a over 2, where a is the start point of the interval, or x0, b is the end point, x2, and x1 is the middle of the segment. And you can see the name of Simpson's 1/3 rule comes from the fact that you divide h over 3 in the expression for the integral. The local truncation error of Simpson's 1/3 rule is equal to this, given by this expression, where e is equal to minus h to the 5th over 90 times the 4th derivative of f of xi, where xi is a sum value on the domain from a to b. We can again also plug in the expression for h to obtain the error in terms of b and a. As you can see, this error depends on the 4th derivative of this function f that is to be integrated. And therefore, if your function is of 3rd order or lower, your error is going to be equal to 0. And therefore, a single application of this Simpson's 1/3 rule is going to be 3rd order accurate. Recall from the trapezoidal rule that this single application of the trapezoidal rule was 1st order accurate because it depended on the 2nd derivative of this function. So you can see we improve the accuracy a lot already. So now we can, to improve the accuracy even more, also divide the interval again up into a number of segments and then approximate the integral by applying the Simpson's 1/3 rule to each segment. So let us divide the interval up into n segments of width h is b minus a over n. And then we can present the integral as this summation. Note that the midpoints of each segment are the odd number x1, x2, x3, or x1, x3, x5, etc. And then we can substitute the expression for the single application of Simpson's one-third rule into this summation to obtain this sum that we can express in sigma notation as this. So it's going to be h over 3 again, and then we'll have this bracketed terms. So you sum over the odd integers of I, and you'll see that these values have a coefficient of 4, and for the even values you have a coefficient of 2. This is the final expression. And again, we can obtain the global truncation error of the Simpson's one-third rule by summing the errors, or the local truncation errors, of each individual segment again. So then we get this. Just the first expression is just the summation over this. And recall, for a single application of the Simpson's one-third rule, you use 2 segments. And therefore, if we have n segments, we apply the single application of the Simpson's one-third rule a number of n over 2 times. Therefore, we sum from I is 1 to n over 2. We can substitute the expression for h into that equation, and again we can write it as an average of this fourth derivative of f, and that is the bracketed terms in the last expression. And again we can apply the mean value, or the discrete mean value theorem, which states that there exists xi in this domain from a to b, such that this average is going to be equal to the fourth derivative of xi. And if we substitute that into the expression of our last slide, we obtain this error for some xi on this interval from a to b. And again, we can take this maximum value that the fourth derivative of f takes on this interval and state that that is the maximum error that we obtain. So the error is bounded by this expression. So we can see that the error scales with 1 over n to the fourth, or we can alternatively say with h to the fourth, so that we can write that this expression, so this is the approximate integral plus this term big O of h to the fourth. So now I'll be moving on to Simpson's 3/8 rule. So the 3/8 rule approximates the function under the integral using a third order polynomial. So here you see this again. We call the third order polynomial P3 of x. And recall from the polynomial interpolation series that we can fit a third order polynomial through 4 data points. If we have 4 data points, this means that the number of segments will be 3. So we can apply Simpson's 3/8 rule through to an odd number of segments, whereas Simpson's 1/3 rule could only be applied to an even number of segments. So often you will combine the two, but we get to that later. So first we can write this approximating polynomial P3 of x using the Lagrange polynomial notation, similarly to the 1/3 rule. And then we can integrate this again to obtain this final expression of the Simpson's 3/8 rule. And as you can see, the name comes again from the fact that you multiply h with 3 over 8. And here the step size h is going to be equal to b minus a over 3, with a and b the endpoints, x0 and x3, and x1 and x2 are midpoints, or are intermediate points in the interval. The Simpson's 3/8 rule has a local truncation error that is given by this expression. So e is minus 3 over 80 times h to the fifth times this fourth derivative of f of xi for some xi on this interval from a to b. And again, we can substitute the expression for h into that to get it, the error in terms of b and a. Again, this error depends on the fourth derivative of the function that is to be integrated, and therefore Simpson's 3/8 rule is also third order accurate, just as the 1/3 rule. Because of this, Simpson's 1/3 rule is usually preferred over the 3/8 because it obtains the same order of accuracy with by using fewer number of points. However, like I stated already, Simpson's 1/3 rule can only be applied to an even number of segments. Therefore, when the number of segments is odd, you can either use Simpson's 3/8 rule completely, or you can combine the two, which is often done. So that is presented in this figure as well. Here we have 5 segments, because we have 6 data points, 6 base points. And then we can apply the 1/3 rule to the first 2 segments and the 3/8 rule to the last 3.